So in 11.3, we'll look at the last way that we'll be counting. It's called a combination. A combination is similar to a permutation in that you're only looking at one group. And you can't use an item more than once, so there's no repetition of items. However, the difference between a combination and a permutation is that the order does not matter. In example 1, we're going to look at 3 problems, and we're going to determine whether they're permutations or combinations. We're not going to solve them. So that should be the first step when you read through the problems, is you should be able to tell whether the problem you're looking at is a permutation or a combination. Part A. In how many ways can you award a first, second, and third place in a car race? So notice it's first, second, third. There's this idea of order matters because there's a specific position. I mean, it really does matter to you, right? Whether you get first, second, third. So this is an example of a permutation. In part B, how many ways can you select 6 free DVDs from a list of 200 DVDs? So here you're choosing 6 from 200. The question is, does the order that you select the 6 free DVDs matter? And the answer is no, it does not matter. You're just taking 6 from 200. So this is an example of a combination. C. Baskin-Robbins offers 31 different flavors of ice cream. One of their items is a bowl with 3 scoops of ice cream, each a different flavor. How many bowls are possible? So is this an example of a permutation or a combination? Well, think about this. You're choosing 3 flavors. Does the order that you choose the flavor matters? And the answer is no. You're going to get the 3 same flavors in your bowl of ice cream, whether you choose, say, chocolate vanilla strawberry or strawberry vanilla chocolate. You still get the same bowl of ice cream. So this is an example of a combination. Again, the only difference between a combination and a permutation is that in a combination, the order that you choose does not matter. We're going to come up with a combination formula. Let's look at this specific example. Let's say that we have the letters A, B, C, and D. So we have 4 letters. We want to choose 3 out of our 4 letters. If this were a permutation, and let's say I chose letters A, B, C, then since it's a permutation, the order does matter. So the choice of A, B, C is different than the choice of A, C, B, or B, A, C, B, C, A, C, A, B, C, B, A. These are all different permutations. However, each permutation has the same 3 letters, A, B, C. So if we're looking at a combination and a combination order doesn't matter, so all 6 of those permutations are considered one combination. Let's say you chose the 3 letters A, B, D. So in a permutation, order matters. All the different arrangements, A, D, B, B, A, D, B, D, A, D, A, B, and B, D, B, A, those are all different permutations. However, A, B, D is just one combination. So you can see that A, C, D, there's 6, but there's only one combination. B, C, D, there's 6 different permutations, only one combination. So since the order doesn't matter in a combination, typically, if you're looking at the same group, there will be less combinations than there are permutations. Once in a while, they'll be the same, but you'll never have more combinations than permutations. It should always be less or equal. Let's come up with the formula. First of all, let's look at this particular example and look at notation. So we had 4 letters. And it's a combination, so we're going to use a capital C. And we're only choosing 3. So that's similar to the permutation, except for we use C for combination. If your calculator has the permutation key, it will have the combination key. So 4C3 is the combination that represents this example. It turns out that there are 4 combinations. I'm going to write 4 as 24 over 6. And the reason why I wrote 24 in the numerator is because I know there's 24 permutations. So I can replace 24 with 4p3. And I can write 6 as 3 factorial. Remember, we were choosing 3. So now when I look at this, I can see that my n is 4, my r is 3, and notice that this is the permutation over r factorial. So let's move on to our combination formula. In general, if you have a NCR, it's going to be the permutation divided by r factorial. So I'm going to replace the permutation with its formula, n factorial over parentheses n minus r factorial, and then that's over r factorial. So remember, these are fractions. This is the same as n factorial over parentheses n minus r factorial. When you divide by r factorial over 1, it's multiply and flip. So just by using properties of fractions, I get to this final formula here. N factorial over n minus r factorial times r factorial. Again, you never have to memorize how these formulas were created, but it's nice to see where they came from. Now in the box we will have our combination formula, where out of the n things you're choosing r at a time. So it's the formula we just came up with. Let's go ahead and use that formula. Example 2. You volunteered to pet sit for your friend who has 7 different animals. How many different pet combinations are possible if you take 3 of the 7 pets at a time? Okay, so the question is this a permutation or a combination? This is a combination. The order that I pick my 3 pets doesn't matter. Okay. Whether I choose cat, dog, bird, or bird, dog, cat, I've still got the same 3 animals. So since this is a combination, I'm going to use the combination formula. Since they have 7 pets total, my n is 7. And since I'm choosing 3 of the 7, my r is 3. In my combination formula, I could simply put in 7 combination 3 if I have that key in my calculator. And when I put that in, I get 35. Or I can do a little simplifying by hand. Remember, this is 7 factorial over, in parentheses, 7 minus 3 factorial times 3 factorial. So 7 factorial over 4 factorial times 3 factorial. And then I can expand this as 7 times 6 times 5 times. I see the 4 factorial in the denominator. So the 4 factorial should cancel. And then times 3 factorial, well, that's just 3 times 2 times 1. And I didn't have to write the 1. Cancel the 4 factorial. Oh, also look, 3 times 2, that's 6. So this is 7 times 5 over 1, and that becomes 35. We'll do another example. Example 3. How many different 4-card hands can be dealt from a deck that has 16 different cards? So is this a permutation or a combination? We're choosing 4 from 16. Does the order that you get the 4 cards matter? And the answer is no. because you can always rearrange the cards once you have the hand, right? So this is an example of a combination. Since it's a combination, I'm going to use my combination formula, where N is 16, R is 4. This becomes 16C4. In a calculator, you should have 1820. If you're not using your calculator and you're doing this by hand, then you would have 16 factorial over 16 minus, you're choosing 4 factorial, times 4 factorial. So 16 factorial over 12 factorial times 4 factorial. 16 times 15 times 14 times 13 times 12 factorial is where I'll stop, because it'll cancel with the 12 factorial in the denominator. And then 4 factorial is 4 times 3 times 2. And I don't really need to write the 1, so I'm not going to. Cancel our 12 factorial. And then you can just plug this in a calculator. Let's see, 4 times 8, divide by 3, 4 times 8 is 12. I could do 4 times 2 is 8. 8 goes into 16 2 times. And 15 is divisible by 3, so this would be a 5. 2 times 5, that's 10 times 14. 140 times 13. Is that 1820? And it is. Our last two examples of this section, these are probably the most difficult combination problems there are. So let's look at example 4. There's a zoo. It has 6 different snakes and 5 different lizards. I have to be careful here because I have these two groups. I have the group of snakes and I have the group of lizards. Now total I have 11 animals, but we got a group of snakes and a group of lizards. 2 snakes and 3 lizards will be selected for an animal exchange program with another zoo. How many collections are possible? So since this is more than one group, I have to be really careful. Now remember, whenever we have more than one group, it's actually what we did in 11.1. It's a fundamental counting problem, but this is also a combination. So when I'm choosing 2 snakes and I have 6 snakes, of course the order that I choose these 2 snakes doesn't really matter, because I'll get the same 2 snakes regardless of the order that I choose my first and my second snake. So it's not a permutation, it is a combination. So what I have to do is look at how many ways I can choose 2 snakes from 6 snakes, which would be my group of snakes, and then I'm going to have my group of lizards. So out of the 6, I'm going to do a combination of choosing 2 snakes out of 6. Now when I look at the lizards, I'm going to have a total of 5 lizards, but I'm choosing 3. So out of the 5, and it's still a combination, I'm choosing 3. So each one of these groups will give me some number, but since I have 2 groups, I'm also going to have to go back to my fundamental counting principle in section 11.1 and multiply those final combinations together, because that's what we do in 11.1. When we have more than one group, we multiply the 2 groups together, the items in the 2 groups. So to figure out the ways I can choose the snakes, it would be 6C2. It turns out to be 15. And that's how many ways I can choose my snakes. How many ways I can choose my lizards? 5C3 turns out to be 10. So now I have these 2 groups. And how many ways can I choose the snakes and lizards? I would multiply those together to get 150. Again, this is probably the most difficult counting problem there is, because I'm actually using a combination with fundamental counting principle. Let's try this again. Last example of this section. A committee consisting of 3 men and 3 women needs to be formed from a group of 10 men and 8 women. In how many ways can the committee be formed? Okay, so I need to choose 3 men from a group of 10 men. So I do have men. And the other group would be the women. And I have to choose 3 women from 8 women. So first I have to figure out in how many ways I can choose the men. It's a combination because I'm just choosing 3 from 10. Order doesn't matter. It doesn't say, well, in how many ways can you pick a president, vice president, secretary from the 3 men? There's no position there. So it's a combination where I'm choosing from the 10, I'm choosing 3. And then with the women, I have a total of 8. It's still a combination. So out of the 8 women, I'm going to be choosing 3. Once I figure out how many items are in the group of men and how many items are in the group of women, then I go back to 11.1 and I just multiply these two together. So I'm just going to use my calculator to do 10C3. That gives me 120. 8C3 gives me 56. When I multiply these across, I get 6720. So again, probably the most difficult type of counting problem. And this is actually the end of our counting problems, the 11.1 through 11.3. We're going to start our permutations in 11.4.